This is GM Word of the Week, and I'm Fiddleback. Lightning. As we've mentioned before, we at the Word of the Week play a lot of video games. Most of our knowledge of the natural world actually comes from video games. Well, it comes from research inspired by video games, because video games don't reflect reality nearly as much as you might think. Shocking, right? Take mountains, for example. There are basically two types of mountains in video games. The impassable barrier kind, and the kind that are basically just ground you can walk over that happens to be a little closer to the skybox. Now, it's fair to say that mountains do provide pretty effective barriers, and throughout history, mountains have pretty much defined where humanity stops spreading, at least for a while. There's a reason the 13 American colonies were restricted, for a long time, to the coastal eastern region of North America. And that reason is called the Appalachian Mountains. That name, by the way, is derived from the name of a Native American tribe encountered by a group of Spanish explorers led by Panfilo de Narvaez in 1527. As the group explored the shores of the islands of the Caribbean Sea and the Gulf Coast of America, they encountered a native tribe in what would be described today as the Panhandle of Florida, who called themselves the Appalachian. Because their lands lay in the foothills of the 1,500-mile-long mountain range that divides the eastern seaboard of America from the Mississippi River Basin and the Great Plains of central North America, those hills got labeled the Tierra de Appalachian in the Spanish maps, the land of the Appalachian. And gradually that name became associated with the entirety of the mountain range. Those mountains are one of two north-south mountain ranges that cut North America into thirds. The other is the longer, rougher, higher, and wider mountain range known as the Rocky Mountains. Those stretch for nearly 3,000 miles up into Canada, with their highest elevation being Mount Elbert in modern Colorado. That stands roughly 14,500 feet above the sea level. For comparison, the Appalachian's highest point is Mount Mitchell in North Carolina, and it stands at about 6,700 feet. What's interesting to note is that the Rocky Mountains, the bigger, wider, rougher of the two ranges, is actually also the younger of the two. It formed when the Pacific tectonic plate began sliding underneath the North American plate as that plate spread west. It took about 30 million years for the plate to buckle and crinkle up into the broad Rocky Mountains. That's because the Pacific plate put up a heck of a fight. Now, if you listened to our episode about volcanoes, you know a thing or two about tectonic plates. But one thing you might not know is that there are two different types of plates. First, you have your continental plates. They're older, thicker plates primarily made of granite and can be between 10 and 50 miles thick. Most of them formed around 3 billion years ago. And because they are so thick and heavy, they rise above the oceans and form most of the land on Earth. By contrast, oceanic plates are thinner and younger. They're more uniform, 5 to 10 miles thick and made of basalt. Most of the oceanic plates are only 70 to 100 million years old. And because they're thinner, they lie lower on the surface. And thus, the oceans collect atop these plates, weighing them down. And when they collide with continental plates, the oceanic plates tend to be forced down into the mantle, where they melt and get recycled. But the Pacific plate was pretty resistant to getting forced down due to its relatively low density. It was a bit like trying to force an inflatable raft underwater. Except the raft was a giant slab of rock and the water was a hot, pressured mass of slightly plastic rock. What happened was the Pacific plate ground up under the North American plate for a long way before it was finally forced into the mantle. And it created a huge, crumpled, bulging, wrinkled mass of Rocky Mountains. The Rocky Mountains. That said, it is not unusual for older mountain ranges to be lower and less rugged, and that's because erosion tends to wear mountains down over time. So the Appalachian Mountains have been worn down over the 480 million years since their formation, whereas the Rocky Mountains are still tall, jagged, forbidding, and delightfully young and full of vigor. But our point wasn't to add more to the already overly long explanation of plate tectonics. You're probably sick of plate tectonics. Our point was that video games present mountains as a barrier, which is fair given the history of humanity. But they also present them as fairly passive things. And that is not at all fair, because humans can and do cross mountains all the time. The mountains, for their part, are pretty actively deadly. And we mean that. We're not talking here about the danger of falling off a sheer cliff or steep slope and smashing yourself to bits on the rocks below. We're talking about very active hazards that suddenly turn you from an intrepid hiker or Austrian soldier into a charred corpse or a frozen slab of buried former person, never to be seen again. And some of those hazards are pretty surprising. For example, imagine you're a hiker, hypothetically, making your way across Rocky Mountain National Park in Colorado. In July of 2014, hypothetically. You're climbing the backcountry and suddenly the sky darkens, rain starts to fall, and thunder rumbles. Now, you're pretty high up, and you're smart enough to know that lightning strikes the highest stuff around. Fortunately, there's a nice, shallow cave nearby. Basically a rocky overhang. So you conceal yourself there. And it's working. You're staying relatively dry. You figure, you can wait out the storm. And then, zap! The last thing that goes through your brain is about 30,000 amps at about 1 billion volts. That's enough electricity to keep a light bulb lit for 3 months straight. And it all goes through your body in a second. What the heck? You just got struck by the hammer of Thor itself, the spear of Zeus, the hip flask of Indra. You got struck by lightning in a cave. To understand how that can happen, you have to understand what lightning is, and most importantly, you have to understand its single-minded obsessive pursuit of just one thing: the ground. But to understand that, you have to understand what lightning is made of. That is, you have to understand electricity. And if we're going to explain that, we're going to have to start small. You know, from past episodes of this podcast, if nothing else, that all matter is made up of atoms, and that atoms consist of a tiny hard clump of protons and neutrons surrounded by a cloud of electrons. Technically, it's actually a cloud of possible electrons held in place by math, but we'll save the quantum physics for another day. What's important is that protons and electrons possess a property called electric charge. Now, electric charge is a bit difficult to explain. I mean, we all sort of have some sense of what electrical charge is. It's that plus sign and minus sign on batteries, positive or negative, right? But what does that mean? Well, it really doesn't mean anything except in terms of itself. It's like all those random descriptive words on your Yu-Gi-Ohs and Magics and Pokemans cards. They only matter when other cards say they do. It only matters that your monster card is a goblin card, for example, when someone plays a card that kills all goblin cards. Other than that, a monster is a monster is a monster. Electric charge is kind of like that. A particle has an electrical charge if it is subject to electromagnetic forces. And electromagnetic forces are forces created by particles that have electrical charges. It's all very circular, and seriously, that's all it means. It's just a property some particles have. Electrons, for example, have negative charges. That means they are attracted to anything that has a positive charge and repelled by anything that has a negative charge. Put two electrons near each other, and they will try their darndest to get the heck apart. They hate each other. But put them near a positive charge, like say the charge of a proton, and they will pull that sucker right to them in a loving embrace that can't easily be broken. Fortunately for atoms, there are other forces, called strong forces, that are strong enough to overwhelm the electrical forces between all the protons and electrons. And those keep the atoms properly structured despite all of this attraction and repulsion. So how do you get from this weird love-hate relationship between charges to lighting a light bulb or cooking a hiker in a cave? Well, it's all to do with energy. If you have an electron stuck to a proton, say, it takes some energy to pull them apart and hold them apart. If you do pull them apart and then you let go, they will rush back together. And that rushing back together releases the energy you put in by holding them apart. And if they have to rush together past a bunch of other atoms, and there's a lot of wiggling and jostling and craziness as all those changing forces disturb everything, you can end up with heat and light and all sorts of stuff. Remember, we're keeping this simple. That's all electricity is. It's the flow of electrons from a place where they don't want to be, say a place with a bunch of other electrons, to a place where they do want to be, like a place that has a lot of protons. And whenever you have a mass of electrons in one place, and you give them a path to a place that can absorb a lot of electrons, they will run streaming along that path, jostling everything along the way, and doing all sorts of damage. When there's a free flow of electrons like that, we call it electricity. The problem is, it's not always easy for electricity to flow freely. That's because electrical forces aren't very powerful, and they tend to drop off over long ranges. So the best way to get electrons flowing is to set up a sort of relay race. Create a nice, attractive, positive charge and pull a nearby electron into it. Now that electron probably came from another atom, and that atom has protons. And now that the electron has been pulled off, there's a nice, positive space for another electron. So another electron will fall into that space, and it'll create another space where it came from, and so on. So you create this little cascade of electrons. Basically, each one is shifting one seat around the table all the time. See? But for that to work, you need a lot of electrons that are relatively free to move around. And that's precisely what happens in metals. Metals generally keep a very loose grip on their electrons. They can bump around and change position easily. That's why wires are made out of metals. Substances that allow electrons to move freely through in a sort of relay race, those are called conductors. They conduct electricity. And substances that don't allow electrons to move around, those are called insulators. And now that you understand that, you understand how literally every electrical appliance in your life works. I mean, there are a few small details we're leaving out, but you could probably build a toaster if you put your mind to it now. But what happens when you have a buildup of excess electrons and no path to a nice, happy, positive place? What happens when the electrons get all charged up but have no place to go? Well, you get an electrostatic buildup. Basically, you have electricity that can't go anywhere. It wants to. All those electrons want to get away from each other, and they want to go somewhere that can absorb them. But there's no path for them to relay along because the stuff between them and that positive place keeps all its electrons locked up too tightly to start a relay race. That's exactly what happens in storm clouds. With all the changing of temperature and air pressure and water condensing out of the air and dust and ice particles bouncing off each other, lots of electrons end up getting knocked free from their atoms. They have nowhere to go. So they just amass in the clouds as a big negative charge, growing and growing. And eventually, the ground can feel that charge. Now, in the ground, there's all sorts of ways for electrons to move freely. So the electrons in the atoms in the ground can feel all that negative energy growing and growing in the sky, and they want no part of it. They start moving deeper underground. And that means the surface of the ground becomes relatively positively charged. And this is where things get really complicated. The ground, now positively charged, starts pulling some electrons out of the air above it. The charge is powerful enough to rip the electrons right out of the air, and that creates a little positive space in the air, and electrons are pulled into that space, and so on. And what you have is an invisible stream of spaces pulling electrons out of the air, getting higher and higher, moving mostly randomly but trending upward. And they are happening everywhere under that massively negatively charged storm cloud. That's called a streamer. And they don't just come up from the ground. They can come up from buildings, trees, and even people. And they will generally climb up about 150 feet. Meanwhile, the electrons in the cloud are really hating the whole negatively charged thing. Some of them finally start to just force themselves into the air below the crowd. And they jostle electrons out of the air and downward, and those force themselves downward. And you have this invisible stream of electrons moving randomly, but trending downward. That thing is called a stepped leader because of the jagged step-like shape it generally takes. And they generally form at a speed of about 200,000 miles per hour. Eventually, one of the streamers reaching up from the ground meets the stepped leader coming down from the storm cloud. And when they meet, they essentially create a wire through the air. And all of the electrons can stream downward to the ground along that path. The electricity flow creates a visible flash that streaks back upwards along the same path, traveling at 200 million miles per hour. The electrical discharge cooks the air around it to the tune of 55,000 degrees Fahrenheit, which makes it twice as hot as the surface of the sun. Of course, the surface of the sun is the coolest part of the sun, so don't be too impressed. But 55,000 degrees is still pretty impressive in its own right. The superheated air around the lightning stroke explodes outward, and then, when the discharge is done, the air rushes back inwards. That outward and inward rush creates a crashing, rumbling sound. Thunder. Now that's just a quick and dirty explanation, of course, and that describes cloud-to-ground lightning. Because of complex charge differentials between the tops and bottoms of storm clouds, you can also get lightning flashing within or between storm clouds. That's cloud-to-cloud lightning. And because you can have lightning whenever there's a lot of churning of the air and changing pressure and temperature, you can also get lightning from snowstorms, or during volcanic eruptions, or during intense wildfires. So lightning is sort of an add-on hazard to all the stuff we've already discussed this month. Even stranger, 1 out of every 20 lightning strokes actually originates from the top of a storm cloud, where positive charges tend to gather rather than negative ones. That means the flow of electricity is reversed. Positive lightning tends to be far stronger and more destructive. Worse, positive bolts of lightning can stretch across the sky and strike more than 10 miles from the storm cloud that it came from. Thus, you can have a lightning strike from a clear sky. A bolt from the blue, which is where that phrase comes from. Now, lightning is dangerous. It kills about 2,000 people a year. But surprisingly, around 20,000 people get struck by lightning every year. And it's just that about 9 out of every 10 people struck by lightning survive. That doesn't mean they come through unharmed, though. Lightning can cause severe burns, obviously, and it can stop your heart. But it can also cause some pretty serious damage to your brain and central nervous system. Many people struck by lightning report chronic memory loss, dizziness, numbness, or other neurological conditions. Now, it is said that lightning never strikes the same place twice. And now that you understand how lightning actually strikes, that might ring true. But it isn't. Lightning strikes the same place all the time. In fact, we rely on that fact to protect ourselves from lightning. That's the concept behind a lightning rod. Lightning is just a built-up electrical charge that wants to get to the ground, and lightning will usually follow the path of least resistance. Forcing itself through the air is hard, so the less air it has to go through before it finds a path to the ground, the happier it is. That's why lightning will happily strike a tree, and then complete its journey by traveling through the water in the tree to the ground, usually vaporizing the water and causing the tree to explode in the process. But nothing is more attractive to a lightning bolt than a tall piece of metal sticking into the sky, especially if that metal is attached by cables right into the ground. So lightning will strike the same place twice. It will even strike the same person twice. For example, during the filming of the Mel Gibson 2004 biblical drama The Passion of the Christ, actor Jim Caviezel, who portrayed Jesus, was struck by lightning during filming, along with the film's assistant director, Jan Michelini. And that was the second time Michelini had been struck by lightning during filming. And frankly, if we were involved in filming a dramatization of the Bible and got struck by lightning twice, we'd be rethinking the project we were working on. Because apparently, everyone's a critic. But we're not the first ones to connect bolts of electrical death streaking out of the sky with divine retribution. Frankly, that idea is pretty much as old as the idea of divinity itself. I mean, without an understanding of electromagnetic forces and the atomic structure of matter, lightning is pretty mysterious. What other explanation is there? Thus, lightning was pretty much viewed as the choice weapon of the gods in just about every ancient mythology on Earth. Thor had his thundering hammer, Mjolnir. Zeus had his spears of lightning crafted in a volcano by Hephaestus. But special mention has to be made of Indra, the king of the Hindu gods, who would go on drunken benders thanks to his addiction to the mysterious religious booze of the Vedic priests, Soma. Soma is described in the oldest of the Vedic scriptures as the juice of a plant whose identity isn't precisely known today. Stalks of the plant would be pressed with stones to extract the juice. Then, the juice would be filtered through a wool screen, and it would be mixed with water and milk. Vedic priests would offer portions of Soma to the gods, especially Indra, as part of their rituals, and then they would consume whatever was left over. And it was apparently pretty potent and likely hallucinogenic. While the plant grew on Earth, Soma was actually a heavenly brew. It was associated with the rain and later with the moon, which was believed to be a lake of Soma. The moon would periodically go dark because Indra and the other gods would drink the Soma from the lake. And then the god Soma, god of plants and healing, would refill it. But we digress, because we never explain the story of the completely non-hypothetical hiker who was struck by lightning in a cave in the mountains back in 2014. He was one of two to die that way in the same park in the same year, and just one of many mountaineers who are struck by lightning in the mountains annually, even the ones hiding in caves and under overhangs. And that happens because the surface of the rock is usually saturated with water and more conductive than the deeper rock of the mountains. So when lightning strikes in the mountains, it tends to spread out in sheets along the surface as it makes its way all the way down into the ground. So it will ride along the sides of the mountain and along the walls and ceilings of caves, and then leap into your head and keep going. Yeah, never hide from the thunderstorm in a cave in the mountains, unless the cave is very low and very deep. But that lightning thing? That's just a warm-up to the very active ways the mountains will try to kill hapless explorers. Next week, we will wrap up our little natural hazards month by describing what happens when the entire mass of the mountain itself, or the snow and ice clinging to it, decide it's time for you to shuffle off this mortal coil. This has been GM Word of the Week. It's written and researched by The Angry GM and produced by me, Fiddleback. You can support us on Patreon at patreon.com/GM Word of the Week. You can find more at gmwordoftheweek.com and theangrygm.com.